And we're back. Ran out of storage space. Okay. But again, person in the train car observes going 2D over the proper time. Person on the outside sees the light traveling a much greater distance. Okay. So, which one's correct, right? Well, both of them have to be traveling, in both reference frames. The light has to be traveling at the same speed. All right, and we know that speed is equal to distance over time. So if it's in the same speed and a different distance, that means that they also have to measure a different time so that the velocity of light stays the same. So let's get a little bit of math going. Okay, so this is going to be the path that the light takes going up from the train car observer. This is going to be the path that light takes up from the observer on the ground. And then this is the distance that the car travels in that certain amount of time. And what I have is I've taken those distances and put them in terms of time, right? So distance, all it is just velocity multiplied by time. So you just take that time, multiply it over speed versus speed multiplied by time is giving us distance on this triangle. Okay, so what we're going to do is do the little Pythagorean theorem. Actually, let me break down this triangle again. So again, this is the distance. Actually, I already told you about that. So yeah, light with a speed of c over the amount of time travels this distance. The train car with a velocity v over a certain amount of time travels this distance, and the light from the moving observer's perspective travels the distance d. All right. So what we're going to do is we're going to write out the Pythagorean theorem. D squared plus this whole mess squared is equal to this whole mess squared. All right, and then we're going to do some algebra, and then we're going to solve it for t, because I don't want to waste your time. Then we're going to solve that for t. Okay, so we get that delta t is equal to 2d divided by c squared minus v squared. Okay, now, because we know that, actually, hold on. Okay, next step we're going to do is we're going to take our equation here, and we're going to factor out a c squared from the square root. So from that we get 2d divided by c times the square root of 1 minus v squared over c squared. Okay. And then from there, since we know that c is equal to 2d over time proper, and we have 2d over c here, right? If we rearrange this, 2d over c is equal to time proper. So we get our final equation of delta t is equal to time proper divided by the square root of 1 minus v squared over c squared, right? So we can simplify that down to be delta t is equal to gamma multiplied by the proper time, where gamma is this whole mess right there. All right. So again, to review, proper time is the time recorded by this person right here. Delta t is the time recorded by the observer at rest. Now, since gamma is going to be a number always greater than 1, right? Because no matter what v is going to be, we're going to get 1 divided by a smaller number. It's always going to be greater than 1. that means that delta t is always going to be greater than time proper. All right. This lets us know that the faster you go, the slower time moves for you. So that means, so this is actually a mathematically and also experimentally proven method of time travel. So if you were to go out into space and travel very close to the speed of light and come back, Earth would be a lot more advanced than you were than it was when you had left. Okay. So I don't want to do a bunch of math, but if it takes you like say 40 years to come back to Earth or whatever, Earth would have gone, I don't know, like 100 years or something like that into the future, right? And so this means you'll also age slower as well, right? And this has been experimentally proven, not like time travel with actual people, but they have put atomic clocks into space. One traveling at a very great velocity, and they noticed that one fell behind the slower clock. So it has been experimentally verified. So again, both of these observations are true and valid. Both perspectives are true because of special relativity. So, and again, it's not an illusion. Time doesn't seem to go slower for you, right? For you, time's going at its normal speed. You don't notice a thing, right? Same with this person, right? But when you compare the two, they're off, okay? And again, it's not an illusion. Time actually does go slower for this person right here. Wow. Okay. Now, one more thing that I want to get into is length contraction. This will go pretty quick. So we have a person, let's say that you're going surfing on a meter stick traveling at a very high velocity. The length that you measure the meter stick is going to be known as the proper length. All right, and then we have an observer, again, at rest with a velocity relative to the Earth of 0. Okay. Now, because we know that delta t is equal to gamma delta t proper, right? We've already done that before. That was the time dilation. We get that delta t. Oh, and we also know that delta t is equal to v velocity over distance. That was just that's just, speed is equal to distance over time. It's just sort of rearranged, okay? What we're going to do is going to replace these delta t's with v over distance, right? In this case, it's going to be the distance or the length of the meter stick. So v over L is equal to gamma v over length proper. Okay, we're going to rearrange that to get L, the length observed by this person right here, is equal to length proper, the actual length of the meter stick that you measure, 1 meter, divided by our gamma right here. So we get that length proper, your observation, is equal to, the at-rest observer length is equal to your observation multiplied by the square root of 1 over v squared, minus v squared over c squared. All right, this shows you that the faster you go, the more squished you are to observers at rest. Wow. So, yeah, I'm sorry this went a little fast, but also a little slow. It all depends on your perspective, right? I know it took a while, but I didn't want to take up a lot of your time. I also have limited space on this phone, So if you have any questions, please let me know. Although I've pretty much exhausted the vast majority of my knowledge on the topic, so I might not have an answer. But yeah, pretty cool stuff. Time travel, length contraction, and simultaneity. Pretty crazy. When it, yeah, relativity is pretty crazy. So yeah, and so is this. So is this lecture, right? It would take me a very long time to explain this. It's very hard to do it in this sort of short format, so I apologize. Anyways, I hope you guys have a great summer. I don't know who I'm gonna send this to, but yeah, have a good summer. Hopefully, see you next year. Goodbye, everyone.